Hello everyone, my name is Marinis Dimitrios and I'm a PhD candidate from the Department of Chemical Engineering in Univeristy of Patras, and I will talk about my research which is about composite recycling with plasma processes. First of all, I would like to give you a small introduction about our lab, the Plasma Technology Laboratory, where our research expands over various different sectors. And besides the common plasma processes like deposition processes, surface treatments, and plasma modeling, as of late, we have introduced plasma on already existing methods, potentially enhancing them, or even creating some methods of our own. For example, we have introduced plasma on medicine production processes, on liquid waste treatments, on bacterial deactivations, and on composite solvolysis, which is my research where we talk about. A few things about composites. As many of you may already know, there is a constant demand growth for carbon fiber reinforced composites, and this demand is projected to reach up to 190 kilotons by 2050. And that's why huge amounts of waste have been generated for composites that have reached the end of their life cycle. With the biggest example of all, the retired wind turbine blades, that their waste are expected to reach up to 20 million tons of waste by 2050. Right now, most of those materials either end up on landfills or they are incinerated. That's why in the last few years, many recycling methods have been proposed. Three are the main methods. It's the mechanical methods that basically shred the materials, but with the mechanical methods, the fibers are severely damaged, while chemical and thermal methods aim for the removal of the polymeric matrix and the recovery of the fibers. With a focus specifically on chemical recycling or solvolysis, and specifically on wet oxidation methods. And the first problem that we need to deal with when we start this research was that those retired composites that we wanted to decompose were manufactured like 30 or 40 years ago. In most cases, the chemical composition was either unknown or confidential. And here was the problem that most of those chemical recycling methods, they use specific solvents based on the chemical composition of the material. That's why we need to find a solvent which can decompose most of those unknown materials, regardless the chemical composition, so we wouldn't have to do materials identification. That's why we chose a strong acid, nitric acid, because it is the best oxidizing agent for composite solvolysis, but its disadvantages are the long process times and the after-treatment waste. Our approach to deal with those disadvantages is by plasma assisting the solvolysis, aiming for low temperatures and atmospheric pressure. Overall, our target was to achieve shorter process times with less generated waste and high quality of fibers. A few things about plasma. Plasma is an ionized gas with equal numbers of positively charged ions and free electrons, and can be created through an electrical discharge, which is the application of a magnetic field between two electrodes. A specific type of plasma that we employ in our research is plasma in bubbles, where plasma is generated in the bubble-liquid interface, as you can see in this video. In this type of plasma, there is a really high generation of oxidizing species and radicals within the liquid. But how does the polymeric matrix is actually decomposed? Two are the main reasons. First of all, chemically, because as I mentioned, the active species that are generated in both liquid and gas phase basically attack the polymeric matrix and they oxidize it. Also, the polymeric matrix can be decomposed physically too, because microbubbles tend to explode at the composite surface, thus enhancing the degradation even more. But we'll focus mainly on the chemistry behind the decomposition. And I will give you two examples of two of the most used chemical compositions on polymeric matrices. It's the amino-cured epoxy and the hydrocured epoxy. Those complex networks that are called crosslink networks can be decomposed when some of their critical bonds are cleaved. For example, the amino-cured network can be decomposed due to cleavage of its carbon-nitrogen bonds, while the hydrocured network due to cleavage of its carbon-oxygen bonds. When enough bonds of the network have been cleaved, then parts of the network start to detach, where this is what we call the D-gel point. Now, in typical solvolysis in nitric acid, only a few species participate on those reactions. That's why the degradation steps are very slow. But when we assist the solvolysis with plasma, over 50 different species participate on those reactions. That's why the decomposition of the matrix is much faster. Now here is a really simplified flowchart of our process. Initially, the scrap composites are pre-treated at a less concentrated nitric acid solution. Then the plasma-assisted solvolysis takes place with a more concentrated nitric acid solution and with constant gas flow of air and argon. From there, the carbon fibers are retrieved and are washed with acetone, while during the treatment, small amount of NOx gases are produced, and all the exhaust gases, including air and argon, are led into a wet scrubbing system that we have developed. From there, the larger fraction of those NOx gases are converted back to a nitric acid solution, while in the outlet of this system, we have a gas flow with a really low concentration of NOx that eventually ends up in the atmosphere. Also, the liquid waste that remains in the reactor undergoes a regeneration process where it is mixed with the fresh nitric acid, hydrogen peroxide, and with a solution that we recover from the wet scrubbing system. The heart of this flowchart is the plasma-assisted solvolysis, which has a setup of its own, which is right here. Basically, inside the stainless steel reactor, which is coated with glass, the scrap composites and the nitric acid are placed. Also, inside this reactor, there is a cylindrical electrode, which allows the gas flow in the form of bubbles. This electrode is powered by a 30 kHz generator, and this is how plasma in bubbles is generated inside the solution. With this specific setup, we have recycled large amounts of composites. We have recycled some aerospace scrap right here, and some wind turbine blade scrap right here. And from those two types of composites, we have recovered short fibers. But the unique advantage of this process is that we can recover high length of fibers with rare cutoffs. For example, we have recycled some hydrogen storage tubes, where you can see them right here, where we can recover continuous fibers with length up to 125 meters. In every case, over 97% fibers recovery is achievable. Now, when we started this research, the first thing that we need to test was to see how plasma affects this process. That's why we decomposed the same composite mass with two different ways. One batch was carried out with plasma-enhanced solvolysis, and the other one is just thermal solvolysis. We saw that with plasma, almost 100% fibers recovery can be achieved after 5 hours, while without plasma, only 50% fibers recovery can be achieved after 5 hours. Thus, we concluded that plasma makes this process effective because the plasma-generated active species accelerate the matrix oxidation. After we established that, we want to optimize our process. That's why we had some optimization steps concerning the recycle rate, the emissions, the concentration of the solvent, the process effectiveness, so it can lead to potential scale-up. For example, in this graph, we try to maximize the amount of composite mass that we can decompose a specific amount of solvent. That's why we studied the ratio between the composite mass and the moles of the solvent. From this graph, we saw that there is a decrease in the percentage of mass recovery of the fiber as this ratio decreases, while fast and complete decomposition can be achieved when excess solvent is used for ratios like below 16. Besides the optimization of the process, we try to analyze even more our process so we can fully understand the mechanism behind the solvolysis. Solvolysis is a three-step process that includes the disintegration of the polymeric matrix, the diffusion of the polymeric fragments to the bulk of the solvent, and the liquefaction of the fragments. And solvolysis can be explained by using two equations, the disintegration rate and the mass transport rate. Now in steady state, those rates are equal, and this is how we can extract a general equation right here, which can express the whole solvolysis process. This equation is a function of the coefficient constant that includes the disintegration constant and the mass transport constant. It is also a function of the composite surface area exposed to the solvent, the solubility of the material, and the fragment's concentration in the bulk of the solvent. And basically, the two parameters that determine the efficiency of the composition are the coefficient constant and the solubility of the material. That's why we made an effort to fit our experimental data in this equation. And we can see an example right here. And we have a really good estimation about the coefficient constant and the solubility and how those two change with different parameters of the process. Other than that, here are some of our final products. You can see some short fibers that come from the wheat urban blade scrap right here. And also you can see some continuous fibers that come from the hydrogen storage tubes of either 12 meters or 120 meters. And those fibers are really good quality because we did some characterizations on them. First of all, we did some same characterization. You can see on figure A the recovered carbon fibers, while on figure B the virgin carbon fibers. You can see that the recovered fibers have no surface damage and no resin residuals on the surface, with only 1% drop on their carbon content. But in order to achieve those good results, we need to test various different parameters. And we saw that different parameters of the process can change drastically the quality of the fibers. For example, you can see in figure C some recovered carbon fibers with many residuals on the surface that come from a batch with a too low concentration of solvent. While on figure D, you can see some damaged recovered carbon fibers that come from a batch with a too high power input. We did some mechanical characterizations, specifically single fiber mechanical tests, and we saw that the recycled fibers exhibit 35% higher tensile strength and 5% higher Young modulus compared to the virgin fibers. But someone will ask, how can the recycled fibers be better than the virgin fibers? And the answer to that is actually heavily mentioned on the literature. And it is because nitric acid and plasma can smoothen the surface by etching away defects and impurities, which can otherwise initiate cracks under tensile stress. Besides the characterizations, we try to compare our method with other recycling methods. And we found out that the energy demand and the cost of our process is comparable to the other methods, but the GWP is still very high, so we need to do some more optimization. Other than that, the capacity of the plasma enhanced solvolysis is already really high, so it can be helpful in a potential scale-up. Concluding, plasma-assisted solvolysis can achieve over 97% fibers recovery faster and with lower working temperatures compared to the other chemical recycling methods. The recycled fibers showed no damage and no residuals, and they can retain the original mechanical properties. We had some optimizations concerning the composite mass to solvent ratio, the recycle rate, and the process effectiveness, and the solvent losses. Overall, our future goal is to reduce even more the generated waste. We have some publications on this matter, you can check them out. And also we have participated on some conferences, with the latest one on the 21st European Conference on Composite Materials in France. And this research is founded by two projects, one European Union's project under the name Eurocomp and one national project under the name Salvage. Thank you for your attention.